me demandais, mais qui c'est c'est quoi ce grand sage qui vient nous observer, qui écrit des bouquins et donc son dernier livre, je l'ai regardé avant de faire cette introduction, et j'ai noté des mots qui ne sont pas habituels quand on parle de nos sciences. J'ai noté des surprises, j'ai noté frustration, j'ai noté deviner, la confiance, et je trouve ça super en fait d'amener ces termes-là aussi dans notre science hautement rationnelle et physique, qui est la modélisation du climat. Et il y a une dernière citation qui m'a beaucoup marquée. Elle dit « The key challenge is to convince scientists to adopt a new scientific goal ». Et je trouve ça super parce qu'en effet, peut-être que le plus gros problème, c'est pas de résoudre la physique du climat, mais c'est en fait de se parler à nous-mêmes et de trouver des objectifs en commun. Et donc j'espère que ce séminaire pourra nous accompagner collectivement, autant que nous sommes, depuis toutes nos disciplines différentes, à trouver des objectifs communs et à réussir à les adopter. Donc n'hésitez pas à avoir des interactions, à envie de dire des choses, de commenter, de poser des questions, en français et en anglais. Le talk sera en anglais, mais je traduirai les questions à la fin si vous êtes plus à l'aise pour les poser en français. Et Steve est avec nous pendant un petit moment, donc on arrêtera dans 1 heure et vous aurez le droit de quitter la salle. On n'a pas verrouillé la clé, mais si vous voulez rester un peu plus pour interagir, dans le groupe ou bien individuellement, je pense que ce sera très apprécié. Donc voilà, Steve, your turn.
Ah, merci. All right, well, I'm delighted to be here, and I apologize for presenting in English. Ma français, c'est très mal. Do feel free to stop me and interrupt, especially if there's anything that you want me to repeat, explain more carefully. I do like it when people interrupt and ask questions during the talk. We can go in whatever direction we like. So, my background is, I originally trained as a software engineer, but I was always much more interested in people than machines. And so although at the University of Toronto, my appointment is in computer science, I'm an unusual computer scientist because I'm interested in how people use computing. And I got into the world of climate modeling, it's nearly 20 years ago now, but through that route of studying how people write the code, how teams coordinate to build complex models. And once I'd started studying climate modeling, the whole field is so interesting. I spent the rest of the 20 years in that world. And I ended up writing this book largely because I realized there's a gap in the literature. There are very few places where you can find a description of what climate modeling is all about that doesn't start from, here are the equations of motion for the atmosphere and let's build up mathematically what modeling the climate system is all about, what modeling the Earth system is all about. And especially for people who are put off by equations, that's hard. People are not going to pick up these books. And yet, this is of massive societal importance. We're making huge decisions about transforming society on the basis of this science, and very few people outside the climate modeling labs kind of know where that science comes from, how it's done. What does it mean to run an experiment on a climate model? Even the word model means different things in different communities. I go and talk to my colleagues in statistics, and to them a model is a summary of data. You go and talk to physicists, and that's not what a model is. A model is something very different. They're kind of used in the same way, but the philosophical underpinnings are different. So when you say I'm using a climate model, people might understand that in all sorts of different ways without really understanding kind of what's inside the box. So that was the goal. Hang on, that was the goal in writing the book. So yeah, here we go. I got it. All right, I'm confusing myself now. All right, so having spent a number of years hanging out in climate modeling labs, understanding the models, getting to know the teams that built them, I realized what I wanted to do is put it all together in a book but in a way that would be understandable for people that have never set foot in a climate research lab. So my audience, as I'm writing this, are people, I talked to a few folks in the publishing world. I said, how general do I have to make it? How understandable do I have to make it? And they said, well, bear in mind, there are lots of people that will never pick up a non-fiction book and read it out of interest. So, okay, I don't have to speak to that audience. But I'm speaking to an audience in the book who do enjoy reading non-fiction, who enjoy reading about science, but don't necessarily have any background in the scientific field they're writing about. So I've tried hard to avoid jargon. There are no equations in the book, although if you're interested, I snuck a few into the footnotes, because I think the scientists that are reading this, they'll want to know what I'm talking about. But I've tried as much as possible when there's a key equation that I want to talk about, to give the intuition. What are the relationships that that equation expresses? And kept reminding myself, how would I understand it at the gut level rather than up here? So how would I explain it to people who are put off by equations? And having written the book for an audience kind of who know nothing about climate science, I've then realized in talking to a lot of my climate science colleagues, the folks in climate science like the book as well. And I don't know if that resonates here, but people kind of especially in some of the labs that I've studied, keep telling me, your book's fascinating. It tells us stuff that I hadn't thought about the work that we do. So kind of it has that dual purpose, which I like. But have to bear in mind, my primary audience was for people that don't have any background in climate science. Okay, so I've played around a lot with narrative structures in the book as well. And for me, this is hard. I mean, I'm much more of a scientist than I am, let's say, I hang out a lot now these days with humanities folks, with folks from English and so on. But I've had to learn, and I think this is something really important in climate science as well. When we're talking to other audiences, we have to be good storytellers. So one of the things I spent some time doing as I was putting together the book was how to tell the story about the people involved in the field. It's not just the science, it's not just the models, but the people themselves and their backgrounds. So where they are, how they interact, and so on. I had a little sticker on my computer while I was writing the book to remind myself. I said, put yourself in the story. So I talk a lot about like my adventures, kind of visiting the labs, my learning process as I went into this field, originally knowing nothing and kind of observing, which for a scientist is hard to do. We're trained not to use I, not to use the first person when we talk about our science. So for me, that was a learning process as well, and it's interesting. And then I used narrative hooks. Like each chapter in the book, I've started with like a key question that I hope is a little bit of a mystery. And like, how did this scientist at this particular moment in history realize even this was an interesting question to answer? And then where did they get their data from? Where did they get their ideas from? And I've used kind of flashbacks to say, well, this is where the original ideas came from, and here's how they developed. So hopefully, you guys can tell me how well it works. Hopefully that draws in the reader as well and keeps them interested. Yeah, okay. All right, so as I was writing the book as well, a whole bunch of key themes emerged. And so throughout the book, I touch on these. One is just, no matter how much when you talk to folks in climate modeling labs, they're always worrying about model weaknesses. Like the model can't do this, it gets this wrong, it shouldn't be used for this purpose because it's not resolving this particular physical process. But when you step back and you look at the history of the field, the idea that we can simulate across the whole planet movements of heat and mass, the interactions between the different parts of the Earth system, it's an incredible engineering accomplishment. Truly an incredible engineering accomplishment, and yet it's invisible, it's inside the machine. You can't see the code well, you can, you can play with the code, but folks outside the lab aren't even going to understand what that means. So it's kind of an invisible kind of engineering, and I wanted to show that off. And the history of the modelling is closely tied with the history of computing in the first place. So one of the chapters of the book, I talk about the birth of modern numerical weather forecasting, which kicked off in the late 1940s with the birth of electronic digital computers. And in fact, the very first programmable electronic computer, ENIAC, at the University of Pennsylvania in 1948-49, one of the very first programs that was ever run on that machine was a weather forecasting program, because John von Neumann, who was kind of, we think of him now as the grandfather of modern computing, of the modern computer architectures, he was a numerical mathematician. He realized that these new machines would allow him to do something he'd always wanted to do, which is run numerical algorithms and solve these complex mathematical problems. And he realized that weather forecasting was this would be the killer app for these new machines. And so he persuaded the army to fund a weather forecasting program to run on ENIAC. And then as you go forward in history and you look at the growth of supercomputing, for example, weather and climate modeling labs have always been at the forefront of pushing those machines as hard as we can to get as much computational power out of them. So the growth of the modeling has been limited at every stage in history by what you can actually do on the machine. And every time you get a faster machine, it's great. Now we can put more things into the model. The second theme is this notion of interdisciplinary collaboration. So the climate model itself, or the Earth system model, I should say, becomes a focus for how people in very different scientific fields can come together and collaborate. And I've been in enough meetings now with interdisciplinary groups trying to talk to each other and having misunderstandings, kind of talking past each other, realizing maybe fairly late in a long meeting that key technical terms don't mean the same thing to scientists in different fields. My favorite example of this, I mention it in the book, many years ago at an EGU conference, I sat in on a meeting of geologists who were working on a single integrated geological map of Europe based on all the national geological maps. So there's like 25 people in the room from 25 different European countries talking about how they can integrate the map. And they realized they'd got probably more than 25 different definitions of the word bedrock. And I think if geologists can't even agree on what bedrock means, what hope is there for the rest of us? So the climate model, though, when it's used as a basis for collaboration, forces you to be explicit, because when you put something into code, you have to be absolutely explicit about exactly what you mean. The program code has a very precise meaning, very precise semantics. And so if you want to understand, well, what does some other scientist in some other field actually mean when they talk about this thing, you can turn to the code and it says, oh, okay, that's how they interpret what they mean by this particular process. You can run the code, you can look at the code, and it becomes this place that allows us to get over those misunderstandings when we just use normal language. So the code has that supporting collaboration process. And then, of course, this one, almost every presentation I see on use of climate models puts that quote in. That's George Box, the statistician. All models are wrong, but some are useful. Yes?
Going back to that sentence, whether the normal way of doing science, maybe my English is not here. Normal way of doing.
Oh, right. So, yeah, I spent some time in the book responding to something that perhaps outside scientific modeling communities people worry about, like how can you treat a computational experiment as good science? It's like you're not doing anything in the real world. It's a simulation. So how can it tell you anything about the real world? And what I do in the book is I spend some time saying that's pretty much how every field of science operates all the time, whether they're doing computational modelling or not. So physics experiments, you know, simple things like an object sliding down a smooth plane. It's not something that happens in the real world. It's an abstract model of a process in the real world. So it's still a model. Okay, so scientists use models all the time because they allow you to abstract away from the messy world and say something about what generally happens. And computational models just fit into that tradition. So I wanted to kind of get that point across in the book. And then I spend some time towards the end of the book talking about what the models tell us about climate change, especially what they tell us about future pathways. You know, our ability, for example, to stay within the UN's 2 degree or 1.5 degree thresholds, and what that would take, what the pathways are to get there, and how we can be sure of that, and how we use the models to understand uncertainty in those kinds of questions. All right, so that's...
Sorry.
Yeah.
About this sentence, climate model is not necessary to prove anthropogenic climate change. I mean, as you said, climate models are used to perform experiments, in fact,
right.
Because we are scientists and we have to perform experiments when we have hypotheses, and because we are working on the Earth, we don't have a B planet, so we have to do experiments another way, right?
Yes.
And so, well, we can do small scale experiments, but we want to have the largest possible scale experiment, and we use climate models.
Yes.
And in fact, I regularly do give talks in front of pupils and people, etc. And my slide where I say, here I prove anthropogenic climate change, is based on model results.
Okay, all right. So there's a dilemma here, right? Because if you're talking to folks who are skeptical about climate change, and if you say, I can show you my computational model, and that demonstrates how we know it's human caused. For us as scientists, yeah, absolutely, that makes complete sense. For people outside the field, it's like, well, how can a computer model prove anything?
I'm not sure I agree, because we do have uncertainty, and we do have, I mean, we are able to, we have uncertainty in the climate model, and we can, I mean, we have the best way we have today to estimate, quantify this uncertainty.
Yes.
Which is possibly not perfect, and we have signals that are beyond this uncertainty.
Yeah, we're not disagreeing. The point I wanted to make is you can build the case for that climate change is anthropogenic through a whole bunch of other things as well, through direct observation, through paleoclimate studies, without resort to the computational model. The computational models add a huge amount to that. But if you want to convince somebody that yes, it is human caused, you don't actually need the models. That's the point I was trying to make. The models allow us to put it all together and say a whole lot more and explore the detail.
This is why they can answer to climate. They are a good answer to climate change.
Yes, exactly. All right. Good. All right. So the basis for the book really started out from 4 studies at 4 different labs, most of which I did around 2008 to 2010. So some of my observations are a little out of date, and I've talked to folks at these labs since then and talked about over the 15 years since I did this work, here's how our models have changed, here's how our teams have changed. But what I do in the book is I use those 4 case studies to anchor 4 chapters where I can talk about that particular lab, kind of characterize who works there and what they do, what kinds of scientific questions they're trying to answer, but I can also use them thematically to talk about different aspects of the modeling. So where are we? So here's the outline of the book. It took me a long time to get to this outline. I tore up lots of different ways of structuring this and played around with it. So the first half of the book is primarily historical. I start off with what I think, and I characterize this in the book as a landmark report in climate science, the 1979 Charney report. And for one very specific reason, because that was the first place where people started to compare different models. So instead of kind of each scientist or each modeler writing and publishing papers to say, we run experiments in our model and here's what the experiments say, the national academies in the US convened this group under the leadership of Jules Charney and said, let's compare what's going on in different models, and more specifically, let's run exactly the same experiment in several different models and compare what we understand about the model's strengths and weaknesses by comparing those experiments. And that, of course, was the basis for the modern practice of model intercomparison projects. And model intercomparison projects now completely dominate the world of climate modeling. So much effort is put into doing model intercomparison projects. And I talked to folks in other fields outside of climate science, and very few fields do anything like that. Very few fields have a coordinated international effort to define precisely a computational experiment where you can ask different labs all over the world to run exactly the same experiment, give you all the data back from that model, make it all available to the community to analyze. Now, some other fields have started to pick up that practice. For example, in biology, in genetics, for example, people do that.
Human Brain Project.
The Human Brain Project does that. Climate science was the first, really, to turn this into a standard practice. And it's really important because it changes the nature of what modeling is all about. Anyway, I had great fun tracing the history of climate modeling all the way back to the 1890s to Svante Arrhenius, a Swedish scientist who was the first person to put together a computational climate model. It's a very simple energy balance model. I'll tell you more about it in a moment. But one of the things that I was struck by reading lots of histories of climate science is that they all talk about Arrhenius, and they all talk about how he said that if you double carbon dioxide in the atmosphere, you would get 5 to 6 degrees of warming, which is not that far off modern IPCC estimates. It's a little high, perhaps. It's on the high side. But none of them tell you what his model actually did. And there are a few people that have looked into it, but very few people I've come across actually know what Arrhenius' model was, like what was the basis of that computation. So I thought, great, I'm going to tell that story. I then jumped forward in time to the birth of numerical forecasting in the 1940s and those original experiments with ENIAC, John von Neumann and Charney, who worked out the original equations for that model. And then that leads nicely into the birth of global circulation modeling and the discovery of chaos theory, and that kind of understanding of the difference between trying to forecast weather and trying to predict future climate change, which are very different kinds of problems. And it's not really until you understand how chaos theory plays out that you understand why they're different kinds of problems. And then the second half of the book is these 4 case studies. And as I said, each of them is thematic because although I introduced one of the labs, I use that to tell a particular story about the model. So for example, when I talk about IPSL, that's my chapter in which I really get into the architecture of Earth system models, the problem of coupling. Partly because that's where I first encountered the problem of coupling. When I first came here and chatted to the NEMO folks, it was because I was studying the UK Met Office at the time, and the UK Met Office was in the process of adopting the NEMO ocean model to use in their operational forecasting, and we're having all sorts of problems coupling NEMO with their atmosphere model. I thought that's a really interesting problem. Why is it hard to couple an ocean model to an atmosphere model? So I dived into that and kind of explore the problem of coupling. Yes?
I have a question about chaos theory.
Yeah.
I'm a student and I've never heard about it. So
Ah.
can you explain a little bit, please?
Okay, all right. So maybe, you know what? I'm gonna jump around a little bit. We can go in any order. Let me just I'll come back to Arrhenius. I'll tell you a little about him in the first place. But let me jump forward in time to this story, and this might help. Okay, so we're going back to, this is mid-1950s, very, very early numerical weather forecasting models. Or maybe I'll go back a step and introduce those as well. This is yeah, maybe this is the right place to start. So yeah, here's a picture of ENIAC, room-sized machine that you can now simulate on a cell phone in a tiny fraction of the time. So that first weather forecasting run on ENIAC, it would take about 48 hours to compute 24 hours worth of weather. So it's not a forecast. By the time the run is done, the weather's already happened. But actually, when von Neumann and Charney first saw those results, they were really excited because they had that immediate insight. If we had a faster machine, we could do this faster than real time. And of course, within a few years, they did have a faster machine and they could start doing it faster than real time. As a revolution in weather forecasting, this was incredible. Within 5 years, the US Weather Forecasting Service had an operational numerical model up and running. So within 5 years of that first run, that was really fast adoption of this technology. Von Neumann, of course, persuaded the US Army to fund all this work because they said, if you can do weather forecasting, that gives you a battlefield advantage. He basically told the US Army this was a key military strategy to be able to do weather forecasting. So, all right, so they've got this very simple weather forecast model. It's a single layer model. So this was the grid for that first, so it's not a global model, it's a regional model. This was the grid for that model. And if you don't know how weather forecasting model works, perhaps the simplest way to think of it is you've got all these grid points, and at each grid point you've got temperature, air pressure, wind speed in 3 dimensions, you've got humidity, you've got about 7 variables that you're keeping track of, and you're calculating at each time step what the rate of change is in each of those variables. And the way you do that is you look at each grid cell and you say what's going on in the neighbouring grid cells. If there's a higher pressure on one side and a lower pressure on the other side, the air is going to move. And so you compute the rate of change for each variable on a time step that might be, say, 1 hour or 3 hours, and then you just keep running the simulation forward in time, at each time step calculating how those variables are changing over time. And that's how you calculate the weather. Step forward a few years, and people start to realize, this is Norm Phillips, who was the first one to do a global model. He said the problem is with that weather forecasting model is that if you keep running it over time, beyond a few days, you've got a boundary on your grid, and you don't know what's going on in the region outside the boundary. So it's kind of like all those errors at the boundary march inwards at each time step. So as you keep going forward, the weather forecast gets less and less accurate, and after a couple of days, it's useless. And they said one way of addressing that is to not have boundaries on your grid, do it as a global model. So what he did is he took that very simple original Charney model, and he wrapped it around. He basically wrapped the grid around so that one side touches the other side. He didn't bother with realistic geometry of the poles because you get this grid convergence problem. All the grid lines converge at the North Pole and the South Pole, and that messes up your numerical algorithms completely. So he said, I'll just avoid that problem. I'll treat the Earth as a cylinder rather than a sphere, and kind of put a wall. So on this boundary, it's as though there's a physical wall, and kind of air moving against the wall will just bounce back. And so it's not like I don't know what's happening at the boundary, I'm just pretending that things just bounce off that wall. And then he did something really interesting, which is he started his model from an initial condition, not what's going on at any particular moment where you could keep calculating forward to calculate the weather. He says, I'm going to start the model at rest. So all my wind speeds are 0 at the start of the run. And he ran it forward he managed about 1 month before the model crashed. I don't think he ever got much more than a month out of this. but a month was long enough from kind of atmosphere at rest, running forward with realistic gravity, with realistic rotation of the Earth, and he put an artificial Coriolis factor in here, because one of the things, for those that understand atmospheric dynamics, one of the things that matters is the curvature of the Earth, and a cylindrical model doesn't quite work. So he put in an artificial correction for that. And within 1 month, he started to see a realistic jet stream start to form in the model. And this got the whole community hugely excited, because suddenly it was those large-scale atmospheric patterns that we can see on planet Earth can now be simulated within a machine. Okay? And then we come to, actually, I don't have any slides on this, because the question is about chaos theory. Oh, and I'm blanking on his name now.
Lawrence? Lawrence?
Lawrence, yeah. What's his first name? Ed Lawrence. Took basically one of these models, ran it one day, and wanted to go back and rerun a part of it with some more outputs switched on, because he wanted to get some more outputs out of the simulation. So he started the simulation partway through from a saved memory state. So he put the state of the atmosphere back in the model and ran it forward from that point, expecting to see exactly the same result. And what he saw surprised him, because it started off doing exactly the same thing, and then it slowly diverged from the previous run that he'd done. And he thought he'd done something wrong. He spent ages trying to figure out what have I done wrong? Where have I made a mistake? So that in a completely deterministic algorithm, started from the same state, why did I not see the same thing happen? And eventually, after lots of head scratching, he traced it to rounding errors in the initial state. The machine had printed out 3 places of decimal, but actually memory was holding a lot more precision. So his starting state was almost, but not quite, exactly the same. And so this was really the first, the mathematics of chaos theory had been known for a long time, but this was the first real practical demonstration of it in a simulation. So it's kind of, one way of thinking about it, it's sensitivity to initial conditions. That in a complex system, a chaotic system, if you've got tiny differences in your starting state, over time, they will diverge. And eventually you end up with completely different behaviours. And so that means, that's why we can't forecast weather accurately more than a couple of weeks, because the errors grow. We cannot measure the starting state, today's weather, completely accurately. So what we've got is a rough approximation of today's weather, and we run the simulation forward, and the errors grow. Okay, make sense?
Yeah, thank you.
Okay, perfect. And then, of course, climate prediction gets over that problem by doing what Phillips did. It said, I'm not interested in predicting forward from the current state of the atmosphere. I'm interested in predicting the statistics of weather. So what's the typical case? What are the extremes? What are the averages? And so what you really want is lots of runs sampling across the space of initial conditions, and you're trying to predict the overall envelope of possible weather systems rather than any individual weather system. That was great. That was a little bit of a diversion, but fun. Especially if that answers the question.
Yeah.
All right. So let me. How are we doing for time? Oh, we're doing better. Halfway. So I do want to go back and talk about Arrhenius. And I'll do this very quickly, and then I'll talk about the chapter in the book about ISPL, and then we'll have some time for more questions. So here's Svante Arrhenius. He won the Nobel Prize for he was a chemist. He won the Nobel Prize for his work on acids dissolved in water. But he's also part of, or if I go back one step further, he's part of this really interesting group at the University of Stockholm in the 1890s. They called themselves the Cosmic Physics Society, and radically interdisciplinary group asking big questions about planet Earth. And one of the questions they were asking in the 1890s was about the causes of the ice ages. So this guy, Niels Ekholm, early in 1893, hope I've got the right year, about then, came and gave a talk to the society about his observations about carbon in the atmosphere. Oh, sorry, no, hold on, I've got the right. So Ekholm comes back from an expedition into the Arctic, talking about all the evidence of the Ice Age, and a month later, Högbohm comes and gives a talk about carbon in the atmosphere, and he'd identified 7 sources of carbon in the atmosphere and 3 sinks, including, it dissolves in the oceans, the process of rock weathering absorbs carbon from the atmosphere, and decaying vegetation creates carbon in the atmosphere. So he's talking about the carbon cycle. Remarkably consistent with modern understandings of the carbon cycle. And during his talk, the group asked him whether he thought the amount of carbon in the atmosphere might change over time. And he thought about it for a while. No, he couldn't think of any of his sources or sinks that would cause a big change in the amount of carbon in the atmosphere. But Arrhenius is sitting in the audience and says, wait a minute, you can connect these two things together. Maybe if there was less carbon in the atmosphere, that would explain the ice ages. Uh-oh, what did I do? I don't think I did anything. Oh, it's back. There we go. So he spends a year putting together this model. Everybody thought he was crazy. Like, how could carbon in the atmosphere change enough to change the temperature of the planet? He puts together this model and he comes up with this answer. Actually, if you reduced the carbon in the atmosphere by about a third, so 2/3 of its level, this is kind of pre-industrial levels of carbon we're talking about, reduce it by about a third, that would be enough of a change to explain the temperature difference observed in the ice ages. And of course, it wasn't really until 100 years later, when we drilled down in the ice cores and we started to see that we realized actually he was right, that changes in carbon dioxide in the atmosphere explain a large part of the temperature differences through the ice ages. So here's his model. All right, let me press on. I said there's no equations in the book. I spent ages with this diagram. This was my first version of this diagram. This diagram does not appear in the book. But this essentially is Arrhenius's equation. Focus on the one at the top of the atmosphere. He realized that to model the temperature of the planet, it's the energy balance at the top of the atmosphere that matters. That energy in from the sun must equal energy out from all the ways in which Earth loses energy. And if it doesn't, that's what explains a change in temperature, average temperature of the Earth. And then he models all the ways that energy moves around, particularly some of that sunlight is absorbed by the ground warms up, it radiates energy up to the atmosphere according to the Stefan-Boltzmann equation, which really had only been worked out a decade previously, 1870s, 1880s, was Stefan Boltzmann's work. For those of you who know if you know the Stefan-Boltzmann equation, you'll know what this term is in there. If you don't worry about it, it doesn't matter. But essentially, this energy gets absorbed by the atmosphere. Some of it passes straight through because at certain wavelengths, Arrhenius already knew this, at certain wavelengths, the atmosphere is transparent to infrared energy from the ground, and at other wavelengths, it's absorbed. So what he did is he worked out these absorption coefficients for different amounts of carbon dioxide in the atmosphere and different amounts of water vapor in the atmosphere, water vapor being the other dominant greenhouse gas. You get different fractions of this flow versus this flow. Where did he get that from? It turns out that in the 1870s, at the Allegheny Observatory, a guy called Samuel Pierpont Langley had spent 5 years measuring the infrared from the moon coming down through the atmosphere and recording it at different elevations of the moon in the sky, and recording the local weather conditions, temperature, humidity, and so on at the time of his observations. And because when the moon is at different heights in the sky, it's come through different thicknesses of atmosphere, Arrhenius said, wait a minute, that allows me to compute how much of infrared is absorbed as you pass through different amounts of atmosphere and therefore different amounts of carbon dioxide. So he then kind of comes up with this whole series of coefficients for if infrared passes through different amounts of carbon dioxide, how much of it is absorbed at each wavelength. Okay, so what I did is I took this model. I can't put this diagram in my book. For people that don't want the equations, this is wrong. So this is the, where are we? This is the diagram I eventually put in the book. Get rid of the mathematics and give the intuition. What matters here is we've got infrared from the surface, some of it is absorbed by the air, and some of it passes transparently through the atmosphere. And the amount of greenhouse gases in the atmosphere affect that ratio, and therefore that changes the temperature of the air because it determines how much heat the air is absorbing, and it changes the energy balance equation at the top of the atmosphere. I don't know if that's enough of intuition. You can read the book to get the rest of the story, because there's a whole lot more to it, like what was that data? How did he even know to set up the problem in the way that he did? The other thing he did, which I found fascinating, I found very few other people ever talk about this, is he realized that if you want to do this, you have to repeat that equation for each location on the planet, because it'll be different. Surface temperature is different. Average surface temperature is different across the planet. So he constructs this grid. It's 20 degrees of longitude by 10 degrees of latitude, cutting off the poles. He's got no data for the poles, but he has got data from these massive weather tables that were published at the time that typically use that grid. So he's got these weather tables that will give you, for each of these grid cells, what the average surface temperature is in each season of the year. And he uses that to calibrate his model. He says, okay, well, I know what the average conditions are. I know what the amount of carbon dioxide in the atmosphere is. I know what typical humidity, atmospheric humidity values are for each season. Use that to calibrate the model, and then I'll change those amounts of greenhouse gases and use that energy balance equation to compute the difference. So he's never calculating exactly what's going on the planet. He's only ever calculating differences in temperature in response to changing the levels of the greenhouse gases. Way ahead of his time. For 50 years after Arrhenius, nobody attempted that again. And in fact, his work was largely criticized. People didn't believe it, didn't believe that this could possibly be true. There were several papers published shortly after his that criticized his work and said, there's no way this can possibly be the case. And it really wasn't until the birth of the computational modeling that I showed you a few minutes ago that people started to get interested in this and repeat his experiments and say, you know what, he pretty much got it right. I'm going to leave you with one little hook on that story, which is his model is interesting for another reason. And that's because he got approximately the right answer, but for the wrong reasons. There are two huge errors in his model that roughly cancel out. And I'm going to leave you to read the book to find out what they are, because I don't have time to explain them right now. But it's a fascinating story. All right. So, yes, so kind of this is my summary. Oh, I love the map as well. I love the idea that 19th century climate science was an international collaborative thing. There's scientists in different parts. Well, okay, it's Europe and North America. It's not that international. But anyway, the scientists in different parts of the world adding pieces of the puzzle, and then along comes Arrhenius at the end, draws on all of that work and puts it together in this first climate model. It's a truly fascinating story. Okay, pause for quick questions. Any other questions about Arrhenius's work? Okay, all right, so let's jump forward. So we talked about this. Let me talk about chapter 6, because that's where IPSL comes into the scene. So chapter 6, I called it plug and play, which is a phrase I've heard in a number of different modeling centers. The idea is, in an ideal world, any climate scientist can come to the climate model and plug in the piece of the Earth system that they're interested in. Say I've got let's say I'm a plant scientist, and I'm interested in photosynthesis, and I'm interested in how a changing understanding of photosynthesis affects the climate in a large scale. I should be able to bring my piece of code, plug it into an Earth system model, and run experiments. And so that's the idea. In practice, it's really hard. It's really hard to plug a new component into an Earth system model. And it's really hard for lots of interesting reasons. So I use this chapter to explore that. As I said, one of my starting points for this chapter was that struggle that the UK Met Office was having plugging the Nemo Ocean model into their operational forecasting system. But I start the chapter by talking about the physical architecture of this campus. Because when I first came in 2008, this campus was horrible. All that greenery that's out there now wasn't here. It was bleak. It was horrible. It was like a prison camp. And I came back many years later, and all this reskinning had gone on. So the glass enclosures of some of the squares, that was new. That wasn't there the first time I came. All of these new study spaces with the green walls and so on wasn't there. And the point is, buildings can change. Buildings can change in very substantial ways as we realize that they don't now do what we want them to do. We change the internal structure of a building. We might not change the thing that holds it up, the supports, but we'll change the layout. And buildings are designed that you can change some things, like the internal layouts of the rooms, you can change the skin of the building, but without changing the fundamental structure. And the reason to point that out is because software is no different. Large, complex pieces of software are very much the same as buildings. We build them originally thinking this is a great design, and then a few years down the road we realize, no, that design doesn't support what we want to do, so we have to start changing the code. And if you design it really well with a good architecture, you can kind of have the equivalent in a building of your structural supports, your load-bearing walls, that you won't change, but within the structures there are things that you do change. So that choice of architecture really does matter in terms of supporting change over time. And climate models have very long histories. Most of our climate models have 20 or even 30 years of continual development of the same program code. What the model does now is very different from what it did 30 years ago, but the history is still there. It's still really the same program code. It's just been updated many, many times. So I use that analogy between buildings and program code to really tell the story of architecture. It's great fun. So here's one way of understanding that history with respect to Earth system models. Go back to, we talked about the 1950s. By the 1960s and 70s, people are starting to couple atmosphere and ocean models. And I talk a lot in the book about why that first attempt to couple an atmosphere and ocean model proved really hard. And I used the IPSL story to explain that. Yeah, we'll come back to that thought, because that's one thing that I do want to do before I end the talk. And then more recently, more and more of the Earth system has been plugged in over time. And the way this typically works is that groups of scientists who have that specialist area have kind of developed these things independently. And then when they're mature enough, say, okay, now we could bring that into the Earth system model and add it in, because it affects the dynamics of the Earth system, it affects our understanding of climate change, and we need to get that into the model in order to understand more about the big picture, more about how the coupled Earth system works. I spent some time as well in the labs I visited looking for architectural descriptions of climate models. The kinds of things that in my original world as a software engineer I'd expect to see. Software engineers love these architectural diagrams, kind of box and arrow diagrams of the chunks of code and how data gets moved around between them. And in the climate labs I visited, you don't get many of those. You get lots of wonderful visualizations of the outputs of the models. They're up on all the walls everywhere, but not kind of the architectural descriptions. So this is one of the few that I found that I love. This is the Bretherton diagram, dates back to the oh, I've forgotten when this is, 1990s, no, earlier, late 1980s. At a time when actually most of what's in this diagram wasn't even possible. Models didn't do this. So this was at a workshop where they mapped out what an Earth system model ought to do. And so each of the arrows is a place where a variable has to be passed from one piece of the model to another because it impacts what that model is going to do. So it captures all the key processes and it captures all of these passing data around within the model. No model actually does it quite in this way. Over the years, models have grown to cover more and more of what's on this diagram. So in software engineering terms, I would think of this as what software engineers would call a reference architecture. This is kind of an understanding of what a model ought to do, but doesn't necessarily describe what it really does. You know what, I'm going to skip the little bit on Earth modelling. Oh, yeah, but wait a minute, I'll tackle this question. All right, so why is it hard to couple an atmosphere model to an ocean model? Oh yeah, we are just about out of time. All right, I'll do this last piece and then we'll do questions. The first folks to do this were Manabe and Wetherold at GFDL, Princeton University. Actually, it dates back before 1975. 1969 was their first successful coupling of an atmosphere and ocean model. And they had very, very simple geometry of the planet. They basically said, we're only going to model half of the planet, northern hemisphere, and we're going to say half of it is land and half of it is sea, and that's planet Earth. And the key was to get the atmosphere model and the ocean model talking to each other. And what they realized is that the difference between an atmosphere and ocean largely boils down to properties of water versus properties of air. At one level, the dynamics are driven by the same set of equations. You know, it's essentially Newton's equations and thermodynamics determine how these things operate as fluids, and that's the equations that are at the core of these models. But water behaves differently from air because things operate on a different scale. So, for example, large-scale flows in the ocean are much smaller than large-scale flows in the atmosphere. So you need a higher resolution model to capture the same kind of phenomena. And the ocean moves more slowly. At the global scale, it moves much more slowly. So there's this notion of, I did have it there, didn't I? The ocean circulation patterns where, now the ocean, this is a very simplified diagram, but there is global circulation patterns where if a parcel of water followed the entire path through the oceans, it takes about 1,000 years to go all the way around the planet. So it's a very slow moving flow, which means if you're running an ocean model, you need to run it possibly for centuries to get realistic ocean patterns. Now remember I said that when they first started running these global circulation models, they would start them with the atmosphere at rest. In an ocean model, if you start it from rest, you're not going to see realistic patterns within 1 month. You're probably going to take 500 years of simulation before what you call a spin-up run gives you realistic patterns. So that's what ocean models do. You start the ocean at rest and run it for 500 years until you're starting to see these realistic ocean currents. And now you're ready to start your real experiments. So there's a spin-up run that's done once, and then lots of experiments will start from the end state of that. Now, when Manabe and Wetherold first coupled them together, they realized this, and they cheated. They ran the ocean and the atmosphere models on different timescales. They would basically run 1 hour of atmosphere model, and then send that data to the ocean model, and then run 100 hours of the ocean model, send that data back to the atmosphere, and run 1 hour of the atmosphere model, because the timescales are so different. And it's really weird, right? You've got an ocean that's spending 100 hours responding to a signal from the atmosphere that was only run, this is a simulation time, of course, was only run for one time step. But that's how they got over this kind of difference in the flows. But the other thing they realized was you haven't just got that difference in the temporal resolution of the models, that when they coupled the two models together, their climate would drift. You didn't get a stable climate. It would drift out of stability and very quickly over a longer run to something that's completely implausible for planet Earth. And the way they solved that problem, again, they cheated. They introduced what they call flux corrections at the ocean-atmosphere boundary. They said, okay, the models keep pushing each other out of a stable climate, so we'll just correct for that. We'll correct at that kind of exchange of heat and moisture at the atmosphere, at the surface of the ocean. We'll just correct for it at each time step according to what we know should be the average exchange of heat and moisture. And for 20 years, actually more than 20 years, it wasn't until the late 1990s, every coupled ocean-atmosphere model had these artificial flux corrections in order to make sure it could simulate a stable climate. And at the same time, those models are being used to predict climate change and being fed into early policy making. And there's this whole question, well, wait a minute, if you've got artificial corrections that are designed to keep a stable climate, and you're then running climate change experiments in your model, how can this make any sense whatsoever? So, why does that happen? Why does a coupled ocean-atmosphere model drift out of stability like that? And the first place that problem was solved was here at IPSL, for folks who were trying to couple atmosphere and ocean models together to answer paleoclimate problems, to simulate over very long periods of prehistory big changes in the climate. And for that, you can't introduce artificial corrections. Of course, you're going to get nonsense answers if you do that. So they spent some time studying why all the other models had these flux corrections, why they were necessary, how would you build a model without them? And the answer turns out to require, this is back to what we talked about at the introduction of the talk, it requires scientists to change their goal. So here's what was happening. Atmospheric modelers were building their models of the atmosphere independently of the ocean and testing them and making sure they could simulate what we observe the atmosphere doing. But the atmosphere on planet Earth does not exist without an ocean. So there's no such thing on planet Earth as observations of an atmosphere with no ocean interacting with it. So those tests of an isolated atmosphere model are wrong. If you simulate an atmosphere operating on its own without an ocean, and you say, I'm going to calibrate this so that it simulates what we observe on Earth, you're getting it wrong. You're basically putting in somewhere else in the model artificial corrections for what the ocean is doing essentially as a heat transport. The ocean moves heat around the planet and then re-injects that heat back into the atmosphere. And so if you haven't got an ocean doing that, somewhere else in the model you've corrected for the absence of an ocean. And then it's not surprising, when you take that atmosphere model and you couple it to the ocean model, it's not surprising they drift to a different climate, because both of them have compensating factors for the absence of the other. When you put them back in, you've now got these huge movements of heat that are artificial, and each of them is looking at the other saying, your model must be wrong, because we've tested our model independently and it works, and it's only when we couple to your model that we discover everything's going wrong. It must be you. And the other people say, no, it must be you. And it's not. It's because testing the things on their own actually does not make sense. And so the solution actually turned out to be very surprising. The key was in the atmosphere model to change how clouds and convection are parameterized in the model. Modelers in the audience will know that what that means, maybe others don't, but it's kind of weird. You're correcting for the absence of an ocean by changing how clouds are simulated in the model, and it's largely because clouds affect upwards and downwards movements of heat. And so what you're doing is you're correcting for the absence of an ocean by changing how clouds affect vertical movement of heat in the atmosphere. And of course, what you're doing is you're getting that vertical movement wrong when you test the atmosphere model in isolation. That's probably enough of that story. I'm out of time, aren't I? So let's wrap up. Hang on a sec. I've got. What about one more? Yeah, let's end on this slide. All right. So yeah. So I had fun putting together the book. I discovered a hell of a lot on the way. I got excited putting it all into the book to share it with folks. And if you want to order it with a huge discount, you can right now for the next couple of weeks, because this is Cambridge University Press offering a discount to folks that attended the EGU, but you don't have to attend the EGU conference to get the discount. So if you want a cheap copy, order it now. All right, let's stop there for questions.
So, any question in the room before we switch to questions online?
So really good. So with your last point about running models coupled into account for the Earth's ability to isolate models, often if we just want to study the atmosphere or the ocean, say in the CSM model or the UN, we run the decoupled model. So how do you justify running it with the incorrect corrections if you're just trying to study one system?
Yeah, and there's these practices in all the modelling centres where you move back and forth between running an experiment just in the component that you're interested in and then running it in the coupled system. I think the real answer for this, and I know at NCAR, they've set up their model to make this a lot easier. And actually, I don't know how easy it is in some of the other models. But the ideal is you keep the whole of the Earth system there, you keep the coupler there, but you still have those other modules there, but you replace them essentially with pre-computed solutions. So you've got kind of what we'd call a data model. Let's say you're an ocean modeler. You don't take away the atmosphere, you leave it there, but you have this pre-computed atmosphere, so it's not simulating it, it's just there giving you realistic numbers for your simulation. And that, I think, then overcomes some of that problem. So so the right way to do this is to say, if I'm interested in one module and I don't care about the others, run the simplest possible simulation in those others to give me something, but don't remove them completely. At least that's one way forward. I don't know if that answers the question. Okay.
Yeah, you mentioned the word uncertainty, but you didn't tell much about it.
Yeah.
And maybe you know that currently in the climate modeling community there is a huge debate among people who say, okay, we should go on with this sort of approach, and more than 4, of course, rather 30 different modeling groups, doing their best to come over with all the challenges you exposed and provide one model or one representation, one digital representation of the Earth, the best they can do, and with which they can play around and precisely do these sorts of experiments and tests. Okay, so that's climate modeling in the classical way and the way you describe it here. And then at the moment you have other people who say, no, we should put all of our efforts together, all of our machines together, all of our best knowledge together to make the best model,
Okay.
the digital twin of the Earth, so like the digital image of the Earth, the perfect model. And with this one, we will reduce uncertainties because it will be more accurate than all the other ones that have lots of uncertainties because we don't have enough money to make the best model. And so we should go for that solution and have one single model that fits all purposes on climate challenges, economic issues, deep ocean issues, geoengineering issues. How do you, perhaps your interviews were a bit early in this debate, so I'm not sure people have been talking about this debate when you were visiting the centers.
The debate goes back.
But I'm pretty sure you heard about it, so what's your view on that?
Yeah, I mean, there are several aspects, and there's several ways of thinking about that question. One is a resource question. If we've only got so much money to spend on modelling, how should we spend it? That's one way of answering it. Another way of answering it is from a sociological...
That's a question, that's not an answer.
I know. All right, so one way of thinking about the problem. Another way of thinking about the problem is what matters for a scientific community in terms of, you've got scientists all over the world kind of asking different aspects of the question, what works best to serve them as tools to do what they need to do? And I think you might get different answers depending on how you look at that question. So the kind of the multi-model ensemble, which is the way that the IPCC has arranged the coupled model inter-comparison projects for decades, has that hugely important sociological thing that the modelers are continually comparing their models with each other. And in the comparison between two different models, you get all sorts of insights. Oh, you chose to do it that way. We chose to do it this way. Let's talk about those choices and why they matter. And that's a really rich way of doing science. If you put all your eggs in one basket, you say, we're going to build the single best model, you lose all of that.
But you have less choices to do. That's their argument.
Well, yes, but okay, no, exactly. So I don't think I have a definitive answer. And in fact, I don't think the community should ever have a definitive answer. I think diversity of modelling and modelling approaches matters, but having a high fidelity model to really drill down into some of these questions also matters. And I would be very sad if the community moved entirely in that direction. I think there's richness in both approaches. I don't know if that, there's a much deeper question there, but yeah.
Est-ce qu'il y a d'autres questions dans la salle? Oui.
The title of the book. I don't know why you choose to repeat the word no 2 times in the one sentence.
Oh, this one here. This is one of my favourite phrases. And it's chosen in a particular way. There's another phrase that I like to do. When I go in and hang out with scientists, one of my favourite questions is, and you'll see the same repetition here, tell me what you do when you do what you do. And that's different to asking just tell me what you do. Tell me what you do is a very shallow question, and it's going to get you a very shallow answer. Okay? Tell me what you do when you do what you do causes, partly it's a really weird way of phrasing it, so it causes people to stop and think, well, what the hell are you asking me? And I'm asking you to reflect much more deeply on what it is you're doing, and therefore what it is you're doing when you're doing what you're doing. So that repetition has a really interesting effect when I ask the question. It makes people stop and think, wait, why is he asking it in that way? So I liked it in the title as well. How we know what we know is different from just how we know climate change or what we know climate change. How we know what we know. So I like, there's a little bit of wordplay there as well.
There's a similar one, which is the unknown unknown.
Right, exactly, and it makes you stop and think. Tell me about the unknown unknowns in climate change predictions. Yes, yeah, and it makes people stop. What do you mean by an unknown unknown?
How can I know it?
Yeah, the unknowns that we don't know about.
Right, but this one?
Oh yeah, a simple question. Now that you've written this beautiful book, what are the next steps? Will you continue studying climate scientists? Will you be interested in other modeling communities? Do you have plans?
Well, I don't know. So I'm currently serving as director of our School of the Environment at the University of Toronto, and that's a big admin job. Is anyone in the audience that has an admin job? It takes a huge amount of time, so I don't get a lot of time. But part of my answer is what else am I doing in my research is I've moved much more into looking at climate services. So I'm thinking, okay, all right, spent all these years looking at climate models, but what about the people that are now using projections from those models to answer, to help in decision-making processes around climate mitigation and climate adaptation? And so that's where I'm going next. We're working on a data platform to allow people to take climate model projections and start answering risks and impact questions where, you know, there's this problem that the data sets are too big to download, so you kind of want to do the analysis in the cloud. But more interestingly, there's this problem of if people don't understand where that data came from, they're going to make all sorts of errors in using it in inappropriate ways. So how do you get that knowledge across along with the data so that the data is used where it's appropriate, and where it's not appropriate, people aren't drawing incorrect conclusions? To me, that's probably the next problem that I really want to spend time studying.
So if I can jump in, there's another possibility that you could have foreseen for your future. Now that you've seen how climate modeling centers are functioning, why not building one yourself? And this is something that we hear from particularly the machine learning community,
or
the computer community.
Yeah.
They like to start from a blank sheet of paper right away, and they actually do so every 3-4 years. And after 5 years, the code is considered completely obsolete. And now our codes are already 20 years old or even more. So how do you see this? Of course, there's no, neither opposite extreme solution is appropriate, but do you really think that starting again all over would actually be good, or the heritage is more benefits than cons?
Yeah, that's kind of like the single model question as well. It's a similar kind of very difficult, very complex question to unpack. But I think throwing it all out and starting over again is a huge mistake. I think there is so much kind of tacit knowledge in how we got to where we are with the current generation of Earth system models. So what you can do with machine learning is you can very quickly train a machine learning algorithm to simulate what a modern Earth system model does. Maybe not quite yet at the resolution of an Earth system model, but it won't be long. And you can run it really fast. You don't need to wait like 2 weeks for your century-long simulation. And so it's very tempting to say, okay, throw out the Earth system models, we can now do it all with machine learning. Machine learning algorithms tend to be black boxes. It's really hard to see what the algorithm actually did. It's really hard to interrogate it and say, why did it give you the answer it gave? At least with the way that we do Earth system modeling traditionally, you can pull it apart, you can run pieces of the model in isolation, you can put them back together, you can see how a process that you observed in one part of the model plays out in a coupled system. There's nothing in the machine learning world that allows you to do that. Because if you train a machine learning algorithm on one piece of the model and compare that to what a machine learning algorithm gives you trying to simulate a coupled model system, they're completely different, and there's no way to move between them. So the way I see machine learning playing out in this community is it helps us with some of the things that are really hard in traditional climate modeling, like parameterizations in the model. So a hybrid model where some of your parameterizations are generated from machine learning algorithms, but the overall coupling system is still the same. Brilliant, absolutely. Or bias correction on the output of a model. So you run your traditional model, but you've also trained a machine learning algorithm to understand where that model's weaknesses are and artificially correct for them. That's a really interesting thing. Or dynamic downscaling, faster dynamic downscaling through machine learning algorithms. So there's all sorts of places where I think you can deploy machine learning really interesting ways in this field, but without throwing out the existing Earth system models, kind of bring it alongside and use it where it works.
So by the way, this is exactly what we're doing at IPSF.
Excellent, good.
Yes, there's questions online.
Yes.
If the folks can turn on that video, and but probably we also have to turn on our video, turn on again.
Sandrine Bernard want to ask a question. Sandrine, if you can open your video too. Yes. Thank you, Sandrine.
Hello. So I'm working at LMD, but on other planets. But my question today relates to the history of science part of your talk, where you presented in the 19th century. Research was mostly done by individuals and today by teams. But at that time, in the 19th century, you showed pictures of only men working on that topic. And it's true that at the time, women didn't have access to university and so on. But there is an exception. And actually, I don't know if you are aware, but a few years ago, some people managed to dig up research done by a woman in that period. Eunice Foot, I don't know if you heard of her. I don't know if you talk about her in the book, because she apparently highlighted the role of CO2 as a greenhouse gas on the climate 3 years before Tyndall, actually. There's a story that she presented her result at a meeting, but at that time women were not allowed to present results, so a professor reads a letter she wrote, and it's actually an interesting anecdote, and I was wondering if you knew about it, and if you talk about it in your book.
Yes, I do. She's in the book, and I was delighted. I was delighted to read about her work. I'd actually drafted that chapter before, as you said, that work was only rediscovered recently. I drafted that chapter before I heard about Eunice Foot, and then so I put her in, and I struggled with how her work fits, because all of those histories of climate science certainly that were written more than a couple of years ago, leave her out completely. And so I struggled with how do you understand the impact of her work, and presumably a whole bunch of other people who history is silent about for all sorts of structural reasons. So she did these wonderful experiments with glass cylinders, pumping them full of different greenhouse gases, measuring the temperature, and when she wrote it up, she said she speculated that changes in those gases in the atmosphere could affect the temperature of the planet Earth. And she was really the first person to spell that out, that changes in those gases could explain changes in temperature of the planet Earth. So that was massive. That was a huge observation. Tyndall comes along a few years later. His experiments are a lot more sophisticated, and that presumably is a result of, well, he had the resources. He's a man. He had all those resources, access to grant money and so on. So kind of much more sophisticated experiments, but he was really just replicating her work. We don't know whether he even knew about her work, and it's like really hard to tell. He certainly doesn't cite her. So it's not clear whether he knew about her work or whether they kind of independently discovered this around the same time. But you're right, she was the first person to make that observation. So yeah, I was pleased to see her in the book. One other thing I should say I struggled with, talking about men's contributions to this field rather than women's. When I finished the book, I realized one of the things that I'd done was I'd referred to all of the historical scientists, when I'm talking that first half of the book, by their surnames. So Arrhenius, Tyndall, who else? Charney, and so on. And then all the folks that I met in the labs in the second half of the book, I refer to them as their first names because that's how I talk about them. And I realized a lot of the people I talk about in the second half of the book are women, and a lot of the people in the history are the men. And I think, wait a minute, I've talked about men with their surnames, and I've talked about modern day scientists, a lot of whom are women by their first names. What am I really doing here? Anyway, it was a complex thought for me in terms of how you present that history, how you present who contributed to it, and also how you present these structural barriers that people faced, that some people's work is celebrated, and it's primarily men, primarily white European or North American men, and other people's work gets ignored. And that, I don't think I've adequately addressed that in the book, but I thought about it a lot as I was writing it. So I'm really happy to have that question.
Thank you. Any other question online?
Thank you for that.
No question online, but maybe I want to add a question to Sandrine's one. Sandrine is working on other planets, and you know at IPRCL we are strong because we have paleoclimate scientists and planetologists.
Yeah.
So do you have a comment on that?
No, you know what? It's an area that I have not really looked at. So I'm aware that people run very similar kinds of models for other planets, even, I do mention very briefly in the book, even for the atmosphere of the sun itself, which has, you can model it in the same way. I have not looked at that work at all. So I'm aware of it exists, I haven't explored it.
So to finish, I have actually one last question that you don't mention. It's the $1 million prize of the Navier-Stokes solution. So you speak a lot about the fact that you focus here on ocean atmosphere and the rest of climate because they're based on physics.
Yeah.
You know, the equations are the Navier-Stokes equations. But there's still a $1 million prize for whoever proves there is an existence and continuity or unicity of that solution. So what if, indeed, we are putting together the best we can, but we fail because there's no solution?
Yeah. Do I have a good answer to that? I think my answer to that is the same answer to almost any aspect of the modelling. In order to run any kind of computational model, you have to make simplifying assumptions, no matter where it is. Your numerical algorithm has simplifying assumptions. Your choice of which variables to include and which you say, I don't think these variables are going to matter, therefore I'm not going to resolve them. All of those decisions come together in the model. And we have to keep revisiting them. And this is why I think kind of that model plurality matters, because people will make those assumptions differently or make those decisions differently. So yeah, it's entirely possible that there are issues with the core numerical algorithms that we don't know about that are going to cause problems. On the other hand, if you're able to make successful predictions from the models, and there are many places where over the course of that history, things that weren't known in advance were predicted from the model and 10 or 20 years later discovered from observations. That's what gives us the confidence that even though we know the models are probably wrong in interesting ways, they're still useful. My favorite one is the cooling of the stratosphere versus the warming of the troposphere, which was predicted by Minabe in 1975 and not really measured from satellite data until around 2000 as that's the key fingerprint of greenhouse gas driven climate change that if it was other things you wouldn't get that cooling versus warming. He predicted we should see that, and it wasn't until many years later that we realized that yes, that's actually what's happening. The fact that the model made that prediction successfully, I think, is what gives us that confidence.
True. It could also be that the errors that we're facing now, with how advanced our models are actually coming back from the lack of starting all over again.
Maybe, yeah.
Revisiting the very primary assumptions, even behind the Navier-Stokes equation.
Yeah.
Pretending that all fluid dynamics and thermodynamics and interactions with the carbon cycle are indeed written in this set of equations.
Right.
May actually need to be revisited now.
Yeah. Yeah, and I think they should be. I think there should be, and quite often there is a kind of reconstruct. Oh, the other time that happens is when a lab buys a new supercomputer. I saw this at the Met Office. When they buy a new supercomputer, which has a different architecture, and you need to parallelize the model in a different way, you have to go back to the equations and rethink them. So there are prompts regularly where we do that. And yeah, that has to keep happening.
Let's thank our speaker again. Thanks for also the online.